Good morning to everyone. The Department of Aeronautical Engineering of Hindustan College of Engineering and Technology is organizing the 5 days faculty development program on advancements in aerospace materials, manufacturing, testing, and characterization 2.0. We conducted the first faculty development program on the same topic during January 2022 with more than 300 participants successfully. In the dynamic field of aerospace engineering, staying at the forefront of technological advancements is not just a pursuit, but a necessity. So this year also, we organize the faculty development program in the same area to equip ourselves with the latest knowledge and insights into aerospace materials. This program has been meticulously designed to provide a comprehensive understanding of the materials that form the backbone of aerospace engineering. At this juncture, I would like to convey our sincere thanks to the management of Hindustan Education Institutions for the support to organize this FDP with the eminent speakers. On behalf of Department of Aeronautical Engineering, I would like to give the warm welcome to our respected Principal Ma'am, Dr. J. Jaya, and other professors from Hindustan College of Engineering Technology. Welcome you all. I would like to extend my warm welcome to the first day session speaker, the respected Dr. Chandra, Sekar, Tiwary, Assistant Professor, Department of Metallurgical and Materials Engineering, IIT, Kharagpur. Welcome you, sir. On behalf of Hindustan College of Engineering and Technology, I would like to extend my warm welcome to all the professors, research scholars from various leading educational institutions, industry people to this faculty development program. Welcome you all. Our distinguished speakers will bring a wealth of experience and expertise to the table, promising an engaging and enlightening learning experience. Through interactive sessions, discussions, we aim to not only enhance our knowledge, but also foster a collaborative learning environment. I encourage all the participants to actively engage in the sessions, ask questions, and share your insights. Let us make the most of this opportunity to learn from one another and strengthen our understanding of aerospace materials era. Once again, welcome to this online faculty development program on aerospace materials. Thank you. Have a good day.
My esteemed faculty and honored guest, it is my privilege to introduce the visionary leader who guides us towards academic excellence and innovation, our Dr. J. Jaya. As we gather here today, let us reflect on the words of Steve Jobs, who said, "Innovation distinguishes between a leader and a follower." Under the guidance of Dr. J. Jaya, our college has embraced innovation and set new standards in education. Please join me in extending a warm welcome to Dr. J. Jaya.
Good morning, all of you. Is my voice audible? Yes?
Yes, madam.
Okay.
Yes, ma'am. It is audible, ma'am.
Yes, okay. On behalf of Hindustan College of Engineering and Technology, I would like to welcome all the learned professors, the galaxy of professors, research scholars, and the participants who have gathered here to attend the 5-day faculty development program on advancements in aerospace materials. So this is the second of its kind. The Department of Aeronautical Engineering is organizing this particular faculty development program, and also I'm so happy that 100 plus participants have joined here, and also I heard that many more professors would be joining for this particular FDP. So for the participants' reference, I want to mention the salient features of our institution. Hindustan College of Engineering Technology was established in the year 2000. So it is a 23-year-old institution. Ours is an autonomous institution. We have got 15 UG programs, 7 PG programs, and 13 different departments have got Anna University Research Center. For your information, this particular aeronautical engineering department has also got recognition from Anna University to conduct or carry out research in the in different domains of aeronautical engineering. So, and also I wish to mention that 70% of all the UG eligible programs have got NBA accreditation. And also this particular aeronautical department has got NBA accreditation in that too in Tier 1 category. In this juncture, I would like to place my wishes and appreciation to all the team of faculty members of Aeronautical Engineering Department for their dedication, efforts in grabbing that particular NBA Tier 1 in the first cycle with good marks. They have scored 720 plus marks out of 1000 from NBA. So my congratulations to you all. And also this particular department, they have got the Central Ministry of Aviation's approved drone pilot training center is functioning in HiSet. That is our institution. So those who want to become approved drone pilot, they can spend a week time. They can get a training from this particular center, and they can become a central government approved drone pilots. So that particular privilege is having this department. And also the department is successfully conducting a drone pilot center. They have got UAV club also. Through this unmanned aerial vehicle club, the teachers and some of the students have got actively involved themselves to give training in the futuristic technologies, not only for our own students, but also for the society. Even for schools they are conducting, and even for the professors in other institutions, like even polytechnic teachers and also IIT teachers, they are conducting training. They are giving training in the futuristic technologies. And also one more thing, even the department HOD also not knowing this, I want to convey a good news that coming Wednesday, we are going to sign MOU with Advanced Manufacturing Technology Development Center, which is situated in IIT Madras Research Park. So through that particular MOU, definitely the research perspective and also the students hands-on training exposure and also research perspective in this advancements in aerospace materials and material sciences would bloom like anything. So I wish all the success for this particular FDP. My appreciation and congratulations to HOD and Professor Kamalvendan and Professor Saravana Kumar and all the team of faculty members for having taken the painstaking effort in organizing this particular FDP. So this is a forum where you can exchange your ideas, and also you can able to listen team of faculty members, professors from IITs, NITs, Anna University professors also joining as a resource person, and also professors from some QS rated institutions also going to join in these 5 days. So have a nice day. Have a nice time to spend and enrich your knowledge. Thank you. Thank you all.
Thank you so much, ma'am. It is my honor to introduce our esteemed speaker of today's session, Dr. Chandra Sekar Tiwary, Assistant Professor, Department of Metallurgical and Materials Engineering, IIT Kharagpur. With a prolific career spanning decades, Dr. Chandra Sekar Tiwary is currently working as Assistant Professor at IIT Kharagpur. He has been continuously contributing in research and has published more than 100 papers of international repute. He has a researchation of 7,899 with high index of 161. His research areas mainly focuses on engineering energy materials, advanced materials processing, functioning materials, nanomaterials, high temperature materials, and many more. Without further ado, please join me in welcoming Dr. Chandra Sekar Tiwary as they enlighten us on the revolutionary advancement in building smart aerospace materials through 3D printing. Sir, over to you.
Thank you. Everyone can hear me?
Yes, sir, you're audible. Welcome, sir.
first of all, thank you to organizers for giving me opportunity to discuss our research work, what we are doing here. Just going to share my screen.
Yes, sir, we can share.
Okay, so is my screen visible?
Yes, sir, it is visible.
So, good morning, all. I can understand it's early morning and I am the first speaker. So, I'm not sure what is the time schedule, but as I see in the email, it's 1.5 hours. So what I'm going to do is I would like to have more discussion after the presentation. So I'll try to finish my presentation in 1 hour, and then in 30 minutes we can have the uh, detailed discussion, and that is what the uh, main theme or main requirement of such FDP, where we would like to have more discussion about the work or the future and so on. So and I can understand the participants are mostly faculty who have worked, who are working, or who has wide experience in manufacturing or materials. So I'm not going to go very deep basic and try to uh, teach like regular class. What I'm going to do is I'm going to give you a flavor of research, what our group is doing and what is the advancement we have made in last couple of years. I'll not have too many references or background because as I'm sure all of you are aware of it, but anywhere if you get stuck or if you need discussion on the background, in the discussion session we can spend time on that. Otherwise we'll go ahead and show what our group alone is doing in the different area. So as already taught that I'm Sekar Tiwary. My title I'm going to talk about engineering materials at atomic scale for development of sustainable and automated manufacturing using 3D printing. Uh, and I'm at Kharagpur, the first IIT in the country, which was established just after independence. We have long way. We are going to celebrate our 75th years in soon, and we have already more than 40 departments and centers. One of the largest campus in India for engineering and technology. This is my group at IIT Kharagpur. It's nano engineering group consisting of engineering and scientists from different background, uh, all the way from biology, biotechnology, agriculture, polymer, nanotechnology, and all engineering discipline. The idea of the group to have a multidiscipline is just to bring the good of every knowledge or every field of research and science and try to put together and see how we can modify the materials which can be utilized for different applications. Uh, Before I start, let me thank all the funding agency, national and international, who were generous to fund our group for research, what we do or whatever passion we have. They are very generous in terms of flexibility and also in terms of resources. So when we talk about material in general, this is the one of the this quadrilateral or quadra is generally used very frequently in material community, and some of the journal, this is the logo also, where people talk about materials are nothing but this quadrilateral connects them very well in terms of processing, performance, structure, characterization, and combination of all decide the properties. Uh, and so far, people were all the material work has been around this quadrilateral and trying to interconnect them, try to see what is the optimum of each of the four in order to achieve the best property. But in last 5 years, apart from this, there are important aspects in engine material development has come into picture, and these are first is energy, then comes environment, and the last one is sustainability. I'm not going to talk about any other aspect because automation, waste, and everything comes into this word sustainability. let's look at first energy and just try to understand what we want to say about energy. Now, when we talk about this quadrilateral processing is something which takes maximum amount of energy. So far, people have not talked about how we can optimize processing itself so that we have minimum energy required for fabricating a single component. Now, the idea is there are different methods people started now looking at. So far, people have not really spent much time how to see energy optimization. Now they started looking at it, and most of the energy optimization goes into processing. Then comes environment. We have been producing several metals, composite and ceramic and so on. And again, any processing or any fabrication comes with the impact. Now, so far, no one talked about environmental impact. But now we started looking at how this environment is impacting our whole ecosystem Earth in terms of it can be water, it can be air, it can be soil, it can be any one of these, right? So environment is becoming a big concern. The idea is we have to produce materials, we have to produce component with minimum environmental impact. The last one is sustainability. Now, this particular word was there, and for Indians, we in our culture we have this word sustainability. We don't throw stuff, we try to reuse. It can be your clothes or it can be any boxes and so on. We have in our culture this sustainability word, but in industry or in general, now in material processing, sustainability becoming a big word because people started talking about source of material, started talking about after use where you are going to dispose it. What about the raw material? What is the source of raw material? How we can get it with minimum impact on energy and environment? Or if you're disposing material, how we can have minimum impact on in our environment or in our water, soil, and so on without spoiling anything. Now, sustainability become a very broad term in terms which does incorporate energy, environment as well. Apart from sustainability, also talks about automation, right? If you are making automated fabrication, is it sustainable? Or if you are trying to have more artificial intelligence and so on, is it sustainable in terms of energy footprint or environment and so on? So these three become one of the critical, point of discussion. And my research direction is trying to have each of them, trying to see how we can contribute in all these three directions in the material domain. Now, as the title suggests, we talked about atomic length scale. Now, this plot, I just try to keep very brief on this because here, if you see material in general, there are different length scale, and it starts first with macroscopic structure, bridges and big structures. Now, which comes next is mesostructure followed by microstructure. And now microstructure is something which is shown here. You can see micron scale, you can look at material. Now, you can clearly see there is a clear correlation. You build bridges by connecting individual objects. Microstructure is also consisting of this kind of interconnected structure, can be single phase, multi-phase, can be of different kind of material and so on. But again, here also we start playing around with the junction, interconnects, and try to architecturally try to build them in such a way that we can get optimum mechanical or structural or functional properties. After that comes atomic scale, which is somewhere here. This each individual structure is made of, if it's crystalline or amorphous, they are consisting of molecular atom, and how to put them together decides the properties of the microstructure, and from there we can also take it to macrostructure. Now, the interesting part of atomic scale, it's in the middle of the material understanding, which is based on physics models mostly. Either it can be molecular or atomic scale, where people talk about interaction of individual atoms and try to change this interaction or try to modify this material, this atom individually, so that at the end of the day, the cluster of atom will have a different property or can be tuned the property of this particular cluster, and hence we can engineer rest of the architecture. Now, At atomic scale, the advantage, as I told you, it's in the middle of both. And if you can understand, if you can build a good understanding through current, state of art automation or simulations packages, and you can also, if you can build it right, you can also make it to other side of this whole scale where you can make smart structures. Now, when we talk about this atomic scale, it's not new, but the whole aspect of atomic scale engineering started coming into picture after the discovery of graphene. Now, the word graphene, I'm sure it got enough attention and it's reached to everyone's, any field of research you are working on, you'll have some, touch upon on graphene. And now it's more than 20 years of graphene research, and people are still, people started asking the questions like, what really graphene has to offer in terms of structural material, right? And again, if you look back, the beautiful part of graphene discovery was it's so simple, it's robust, it's easily doable. You can do any part of the world you're sitting, you can take a Scotch tape and try to exfoliate them and get one atomic layer. Now, so far, there are a lot of work people talked about atomic scale materials, but this particular Scotch tape experiment give us confidence that we can not just make them, we can handle this material, right? And that is one of the important aspect of the whole graphene research, which came in last 20 years. But our initiative or our understanding was more in terms of structural application of graphene. And the question we asked, what graphene has to offer us in terms of structural material. And the first part of graphene is you can exfoliate them, and you can see this black block here or here. If you see graphene, you can put them together. First, take graphite, exfoliate them, make them single or couple of layers carbon. Then put them together with the right chemistry, right processing condition. You can make a foam structure. Now, what is foam? Foam is these are mostly blocks with a lot of porosity. Now, these are very different than the plastic or metal foam you use here. The density is way lower than any one of the foam which is existing. It has more than 90% porosity and only 10% or less than 10% material. The density is so low that you can really literally put on a feather of a bird or flower, and they can just they are so light that they can retain there without destroying the base structure. But when you look at the properties, the first time we observed that graphene structure and these foams are one of the only few material, and so far it's the only material which retains its mechanical property all the way from liquid helium temperature, which is couple of kelvins here, to 1100 degrees centigrade. Now, when we talk about aerospace material, or in general aerospace application, the interesting part is in aerospace, the biggest challenge, and all of you will agree on that, is the range of condition the material or the object is exposed in aerospace application is the widest among all, right? You will have places where the temperature can go very low, or you will have certain places where temperature can go to very high. Now, you need a material, and that's one of the biggest challenge in building aircraft or any aerospace material, that you need to have a different zone having different condition. Hence, you have to use different material, and then you have to connect them without any failure, right? That's one of the biggest material challenge in all these applications so far. Now, graphene become one of the interesting material that which retains its properties all the way, and you can see they are stable. They don't destroy. Now, if you look at the structure of graphene, another advantage graphene has to offer is they are atomically thin. So after graphene, you get many more atomically thin material which can be easily put together with this. For example, hexagonal boron nitride is just physically mixed, or you put a solution, mix them, and they can nicely stick to each other or try to stay together. And the simple reason is the surface charge help them to build the structure. So you can see if you have a graphene oxide single layer, they crumble because of its own structural weight or surface charge. Generally, they crumble. But if you put HB in, they become flat, and you can make a much bigger, single layer or a layer of material by putting HBN on graphene oxide. Now, this is just one of the work, but we end up making a lot of this structural engineering, or I'll say atomic scale engineering, where you start putting nanoparticle, another 2D material, and you can tune its structure and hence its mechanical properties. Also, the graphene or graphene oxide has a lot of surface area. Now, the surface areas are very active, so we can utilize them mixed with a very small amount of polymer, and then we can retain the porosity. We compromise a slight in density, but still the surface area we retain very high, and we can make them structurally robust. For example, the example of here, which is shown graphene oxide with PDMS, we make the foam, and foam can have a tensile strength also. Which was completely interesting, because now we can have a high surface area foam with tensile strength, hence it can be more robust as compared to just pristine one. Now we end up, keep on modifying them, and see the whole idea was to retain the low density, get high strength and high surface area. Now, the simple reason for this whole engineering was to have a high surface area structure which can be utilized for either thermal, or it can be utilized for catalysis, or it can be utilized for energy, for example, battery electrode material and so on. Also, this can be utilized for water treatment and so on. So after our work, the whole structure has been utilized for all sorts of application where you need high surface area and you need good structural integrity. Now, graphene can also replace graphite in terms of few of the application. For example, the graphite industry takes maximum amount of energy in processing the graphite blocks. So you take graphite powder, put them together, and in order to sinter them, you need to have a temperature more than 1500 or 1600. And then you sinter the graphite, which can be utilized. Now, the high temperature sintering is one of the major energy consumption in energy consuming component in processing of graphite. Now, the question is, can we take graphene and then try to put them together, and we can achieve a certain property which is comparable to graphite? So what we did, we took graphene, functionalized them with a COH or OH functional groups, and mix them together at room temperature and compact them. When you do that, we can see we can make nicely welded structure of 3D graphene, which has very similar property than graphite, and also it has ductility, which is not there in graphite. The bulk graphite breaks in a small bending, or if some of you, if you know about graphite, handling them is very difficult because they are very brittle. A small impact breaks them. But the structure made of graphene has enough ductility to take some of those shock load. Apart from that, we can easily weld this graphene or this, the structure by spark plasma sintering, where the interface get welded. Now, with this kind of welded, solid structure of graphene, which is very similar to graphite, does have porosity around 50%. Still, it has strength almost like some of the solid material, and the density is way lower. So if you see this Ashby map, which is utilized to see the material performance in structural application, the modulus versus density map is generally utilized. So what we do here, these are the foams, polymer, metals, and so on. The red block here, which is shown, is where the solid 3D graphene structure look like, where the density is lower and strength is above foam, and very similar to most of the plastic. And if you improve it, we can reach to some of the soft metal like aluminum and so on. Now, another interesting application of this 3D graphite is, if you look at the electrical application. Now, this is the strength and electrical resistivity. If you see the current material, the 3D graphene, it shows very good conductivity, almost similar to metals. And that excites a lot of application of this graphite in electrode material. Either it can be big electrode like steel industry and so on, or it can be fine printed circuits also. Now, graphene can be also utilized in processing the ceramic. Now, ceramic is one of the area where people utilize highest amount of energy to sinter them. Now, the question we ask, is it like every ceramic you need to sinter to high temperature? And what they use high temperature is for to connect these individual particles. We took a model example of silicon oxide and try to simply, we just functionalize them initially with certain functional group, followed by mixing graphene. So what graphene does, if you take silicon oxide, put them together, the surface oxygen doesn't like to bring them closer. As a result, they don't stay together. Now, if you put graphene, it acts as a curtain, a barrier, where both side oxygen surface, they don't interact with each other. Rather, they interact with the carbon or the functional group in the graphene. As a result, without any heat treatment, we can make solid ceramic structure, which is shown here. They have reasonably high strength compared to the silicon individual particle agglomerate or even functionalized block. And if you do that, we can make structures, ceramic structures, which are not utilized at high temperature, can be easily reinforced with graphene, and you don't need to put energy there. Graphene can act as a template because it's ultra thin and the transmission is very high. You don't need to, it doesn't compromise any transmission component. So the applications or the utility around you where you need high transmission, you can utilize graphene as a template and then decorate this graphene with antimicrobial nanoparticle. For example, copper oxide, which is shown here, you can see clearly they are nicely decorated on graphene sheet, and this graphene sheet is coated onto those objects where you can get functional application also. Now, another application of graphene is using in composite, and epoxy was one of the examples where a lot of work has been done, where we try to mix graphene, HBN, and this graphene act as a good reinforcement. If you do a right surface engineering, you can make a composite with superior mechanical property and also thermal property. But the question is, the graphene being one of the exciting material, is it sustainable to produce them? And if you look at the market, there are several countries, they started producing graphene at large scale, but major problem in all these cases was the cost, because most of these are produced by multiple methods and so on. And then finally, the cost becomes so high that most of the industry cannot afford it. Also, the know-how of graphene, for example, chemistry, functionalization, has to be unique for every matrix or every component. So with the first challenge of producing graphene in a sustainable way, we took up this challenge, and we thought that can we utilize biggest waste in the country. One of them is agriculture waste. Now, India being one of the major food producers in the world, and as a result, we do produce a lot of agriculture waste. And this is a problem all over. It keeps on coming in news from here and there in the country. This agriculture waste, the simple reason we have to burn them because there is no economy involved here. Now, if you start putting economy here, if this waste is given some value, then I don't think anyone is interested in burning them. Now, the question is, what can we do with this? So we took up this agriculture waste, set up a pilot plant where we do a certain treatment. Again, energy efficient, environmental friendly treatment without any chemical or additives. We do certain thermal and other treatments where we can make them into fine flat flakes. Now, these flakes are, you can see the scanning electron microscope here, scanning electron microscope image here. These are thin flakes. There are 20 to 30% few layer of graphene, amorphous carbon, and graphite. The whole mixture is there. Now, interesting part is this nice flat morphology particles can be utilized to make a composite. Now, Gelens, our industrial partner, they came up, scaled the whole thing up. And what we say is, if you take this green graphene, we call it as a product name, if you put in epoxy, you can coat on steel. And if you do that, you get much nice surface finish. Now, let's look at some of the processing thing which we optimized. We did different temperature, time, and as you increase the temperature, we see a higher surface area, the flakes get exfoliated and so on. And we also compared the coating hardness, Young's modulus, compared to pristine epoxy. The transmission electron microscope shows that if you tune the parameter, we can make very thin flakes and also smaller size flakes into this during the process. And also we really did some initial study and tried to look at, is it really important to have exfoliated graphene in this composite? Now, the surface charge, which is measured by zeta potential, we compare different size green graphene versus exfoliated green graphene. What we see, the exfoliated green graphene has very high surface charge compared to the green graphene. Now, what happens to high charge? They tend to have more agglomeration, and that becomes one of the biggest problem in graphene large scale production, that agglomeration is a big challenge. But in green graphene, the potential is or the charge is moderate, hence they don't agglomerate as compared to exfoliated one, which makes them nicely distributed reinforcement. The conductivity also, we can see exfoliated graphene has lower. Also, we look at the distribution, we can clearly see that if you see epoxy, the industrial scale epoxy, they have a lot of porosity. These are sub-micron level, so you can't see them, but if you look at it in scanning electron microscope, we see this kind of bubbles. Now, what this bubble does, although this epoxy protects your substrate, mostly steel, but if you let it be there for say 10 years or beyond that, these holes become a channel and it helps in corrosion. We mix our green graphene into the structure. You can clearly see as we increase the concentration, these small holes or porosity, they become finer and finer, and at certain concentration, you don't see them. And what it helps in, now the channel for the your charged ions get bigger or become longer. As a result, the life cycle improves. The mechanical property already we discussed, just because of the carbon reinforcement, they improve. But as we have a very fine 2D flakes, the interesting part is the surface roughness. And you can see here the surface roughness from epoxy 3.6 micrometer comes all the way to 1.1 micrometer, which is almost, you can see half of it become the roughness, so the surface finish become better. The corrosion rate is something which we compared here. This is uncoated steel with the epoxy, and these are different percentage of green graphene, and you can clearly see these observe 3 order of difference in epoxy coating by putting this green graphene. And we did several other mechanism study. For example, we did impedance and so on, and try to understand what is happening. At the end of the day, the structure is something which is modified here because of green graphene, which has multiple effect in all our measurements. And hence, currently we are producing 150 kilo per day graphene plant, where we can produce more than 100 kilo green graphene, and which is utilized for paint. Also, we are looking at different water and pipes and other structural application. I have a book on graphene from waste, where we discuss about different methods of producing graphene which can be utilized. Now, this is not the only waste we need to be concerned with. Another big waste problem which is going to come up in another couple of years is electronic waste. And after the digital revolution in India, I'm sure another 4 or 5 years, all around the cities will have a pool of electronic waste. I started working on electronic waste in 2015, where we showed first time that you can take this electronics waste and take out the most complicated component, which is PCB. Now, PCB is interesting because it got all different kind of material. For example, it got metal, it got ceramic, it got polymer. Now, separating them individually is difficult. So most of the electronic waste, they take out the gold and silver and dump rest of them. We take this whole electronic waste, crush them in our ball mill and make them in a powder form. We take this powder, put it in water. The moment you put it in water, the metals settles down and ceramic and polymer remains on the surface. You take this ceramic, take this metal, we can mix it and make composite out of it, metal composite, and the polymer can be utilized to produce graphene. So these are fine polymer, use laser onto these polymer particles, and they become carbon. And these are very conducting carbon, which can be utilized to make any sorts of carbon ink and so on. Another waste is petroleum coke, which is there in petroleum industry. Again, it's very specific to petroleum industry. But again, as India is becoming, becoming a hub for petroleum refining or treatment, we do have a lot of waste. This petroleum coke or pet coke generally can be also utilized to produce more graphene sort of structure, but it has less crystalline, more amorphous, but still it has certain high surface area and other functional property which can be utilized. Moving next in this atomically thin material, MOS2 become one of the popular materials for several application and lubrication and all. Again, this is more related to electronics grade where people can modify the structure and hence change the electronics. I'll not discuss this in detail, but just to tell you, this atomic thin material, the interesting part is here. And what you see on top is the structure, the transmission electron microscope, and any bright spot is a different atom in this 2D material. So, for example, this is OS2, WS2 structure doped with tin. Now, wherever the bright spot, they are tin, which can clearly show that tin, just replacing one or two atoms, we can make different morphology structure or different structure. The stacking of layers changes. Also, we can have phase transformation possible by just doping a small
Sir, excuse me. I think your voice is not audible. Hello? Sir, we could be able to see the screen, but your voice is not audible.
Is it better now?
Yes, sir. We can hear.
Okay. I think it was muted in between.
Maybe, sir.
Okay. Can you hear me, all of you?
Yes.
Okay.
Yes, sir.
Okay. So in the case of layered materials like graphite, like you have a layer, for example, in plane we called it, they have a stronger bonding compared to out of plane. And these two layers are separated by van der Waals forces.
Sir, sorry for interrupting. The video presentation is not visible.
Come again?
Presentation is not visible, sir. Your slides.
Presentation. Wait, let me unshare and share it again.
Yes, sir.
Now is it visible?
No, sir.
No, sir.
Yes?
It's getting ready. Yes, sir. Yes, it is visible now.
Yeah. Give some few minutes. It will, depending on internet speed, it will load. Okay. So you can see the screen.
Yes, sir.
Yeah. Shall we start?
Yeah.
Okay. Good. So we have layered materials, and so far people only explored layered material for exfoliation and say that, okay, if you put energy, you can separate one layer and make 2D material. But the question is, only there are a handful of material which does, or handful of compounds which does exist into layered form. Rest all are in layered. Now the question is, if it's non-layered, can we also exfoliate them? And we started with the natural material, for example, hematite. Now, hematite is one of the ore which is found in earth crust. Major portion, again, India is one of the major hematite producer. Now, interesting part in hematite is, if you see, these are molybdenum disulfide in natural, and this is hematite. Now, the natural hematite, this is how they look like, and you can clearly see they have a nicely layered structure, very similar to MOH2. So in nature, when they deposit hematite, these are deposited layer by layer, and over the time, the lateral size, the lateral grain size, become way bigger than the interlayer spacing. And some of the spacings are separated by organic molecules or living species and so on. And hence, there is a good anisotropy created. Now, this anisotropy can be utilized by a small solvent chemistry where you put a certain solvent, give energy, they can exfoliate into atomically thin layers. Now, this particular work become one of the first work which started exciting people to explore non-layered material for two-dimensional exfoliation. And there are, after this, such kind of material can be utilized for energy, catalysis, sensing, and so on. Now, this inspired us to ask a bigger question in Indian context, where we have, if you go around your state, you'll find several mining is there around us in most of the places in Odisha, West Bengal, Karnataka, Tamil Nadu, Kerala, where they do this kind of treatment. They take out the mines. When they take out the mine, they dump most of the this dust fine, right? Now they create a big problem in environment, especially the whole region become dusty and become a lot of dust particle. If you see these particles, these are nothing but a fine particle which are on top layer of the earth crust. Generally, they are silicates. Now, the question we ask, can we do something with this silicate and try to make use of them in certain way? Now, let's try to understand silicates. There are different kind of silicate. If you have studied in your basic physics or basic material science, now depending on where you are taking out your particle from, they can be of different structure. Now in silicate, the natural silicates, which are somewhere, which is shown here, most of these are artificial silicate. Natural silicate, they exist in a nice layered way. When I say layered means this, what you see triangles are silicon oxygen layer, which is separated by potassium, sodium, calcium, magnesium, and all these different elements. They do exist in between these layers. Now, when they exist in between layer, if you put energy, they have a tendency to break the interlayers and make them in a 2D form. For example, if you see biotite, this is one of the most popular silicate. They are, you can see they exist in a layered form. Now, if you thin them, you can make them transparent. And this is what we started with. We took several of these different kind of silicates and we started exfoliating them. The biotite was the first, where we took the biotite. This is the layer of biotite. We start thinning it up. Once you thin it down, you can see you can make very thin layer of the silicate. If you look at in transmission electron microscope, you can see their structural integrity or the structure periodicity remains there. You do see defects and so on. We can make a fairly large layer of this material, and we can produce in large scale. You can produce grams and kilograms without any problem. The same idea can be extended for other silicates, for example, diopside, tourmaline, and so on. So you can produce different kind of silicate in 2D form, and this can be utilized. Now, silicates being charged to the layer, it can be easily integrated to our, application. For example, fabrics can be coated with silicate. Now, the silicates have very interesting property of high surface charge, and as they are thin, you can apply a small force and you can use them as an energy harvesting material. It can be by tapping, if you bend them, if you put magnetic force, because some of this silicate does have magnetic particles or magnetic elements which are doped or decorated, and also you can have heat and force together can also give rise to energy harvesting. Now, it can be utilized for making smart electronics or smart fabric, which can be utilized for biomedical, defense, and all different applications. Now, also we can, if they are in 2D form, we can utilize them for 3D printing on certain object. Either it can be on your gloves, or it can be on your fabric, or it can be electronics or any object or device which is mounted or connected to human body can also be made using this such kind of material. You can also utilize other natural material, for example, lead sulfide, which is galena, again popularly found around the different mining area. With copper, they are very frequently found galena in the same mines. Now we can utilize them, make them in 2D form. If you make them in 2D form, if you can make them in 2D form, we can utilize them for RF energy harvesting. And what we do here is, if you can put them into a right contact, we can utilize a walkie-talkie. For example, this is the RF circuit which is made here, connected to LED. Now, if you see the walkie-talkie, which can bring, if it goes too far away, out of range, it doesn't glow because there is no voltage. Now, if you bring closer to the RF waves, or immediately they start glowing because they started showing voltage output. Now, such kind of sensitive electronic devices can be made, which can utilize for energy harvesting or non-contact energy harvesting as well. We can start exploring optical materials, for example, pearl, which is utilized for jewelry and decoration and so on. But pearl is another interesting layered material where agonite crystalline structures are separated by organic molecules. We take this pearl, crush them, and then exfoliate them. Once you exfoliate them, they make nice suspension of 2D material. The transmission electron microscopy shown here clearly shows the crystallinity retains with a very thin 1 or 2 layer thickness. And you can see beautiful calcium-based 2D material has been synthesized from pearl. The optical properties are very different than the parent material. It has a lot of exciting optical properties. And as the color of pearl changes, the 2D material also can be tuned or can be modified. And such material can be used for optical application. For example, we can also make a robust laser using this material or 2D pearl. Also, we can utilize some of this 2D material for DNA sensing, or it can be utilized for several quantum application as well. Now, taking ahead, we can also make 2D materials with a controlled composition, where we take certain elements, mix them together, heat them, get the required phase. Once we get this crystal, we can exfoliate into large what you call production, and we can make good lateral size. Also, the thickness can be tuned, and such material can also be utilized for coating on a substrate and utilize them for energy harvesting. Cobalt telluride is one of the example which utilizes the flexoelectric properties. Now, also one of the interesting 2D material which recently we made is gadolinium telluride. Now, gadolinium is a heavy, large atomic diameter element. Mixing with tellurium, we make this compound Gg2T3, and if you exfoliate them, it has a huge surface charge. Now, this surface charge can be utilized for rainwater harvesting. So, if you put rain droplets on this gadolinium telluride, it starts showing the voltage output because of the charge and isotropy. Now you can 3D print into certain substrate and utilize on a roof, and you can also coat on solar panels. Now in rainy season, the solar panel doesn't work. If you coat with this material, you can utilize the same solar panel for energy harvesting or rainwater energy harvesting as well. We have also worked on pyroelectric using silicon telluride, and we also work on a lot of magnetic material, which we'll not discuss here. Now, we'll quickly move to the next stage of work, which is related to metals. And I'll just have one slide here where we utilize multi-element, try to make a single compound or single phase material, which is called as high entropy alloy. Now, there are a lot of work in high entropy in terms of making stronger material, but what we are looking at is trying to utilize this high entropy for catalytic application. And what we observe in our experiment over last 3-4 years, that for example, if you have a copper individual bulk copper versus copper in high entropy, the chemistry or the chemical activity is completely different. And as a result, you can have a nanoparticle consisting of copper. In high entropy stage, it can behave completely different and do a lot of reaction, which was not possible using bulk or nano copper. Similarly, we have made structural metals into a high entropy form like nickel, gallium, iron, and so on, which does hydrogen evolution or oxygen evolution, and also we utilize them for multiple sensing and so on. Now, this is more related to environment, generally we do, but another aspect of making metal 2D also is we can utilize quasicrystal, which can be a source to exfoliate or exfoliate and make 2D metals. For example, 2D aluminum can be made through quasicrystal. If you take aluminum, cobalt, nickel, with cobalt and nickel in a very small quantity, you put them together, do a right surface chemistry, we can exfoliate them in 2D form. And it can be utilized for hydrogen generation, oxygen evolution, and also a lot of plasmonic work can be done using this kind of 2D material. Now, the question is, all this synthesis method, the biggest concern in large scale is the size, the dispersion, the dimensional tolerant into this material. Also, some of you can definitely ask the question that, okay, there are all cool properties, nice things, but what about its environmental impact? We are putting a lot of energy, a lot of chemical here. Now, can we do something, try to have environmental friendly, energy efficient synthesis of this nice fancy material with controlled size and shape? Now, if you want to do that, we have to go back and see what we generally get. In all our CVD or liquid exfoliated, we see this kind of nice 2D crystals. And one of the biggest problem here, you can see in the image, you see a small crystal all the way big crystal. So the dimensional distribution is huge. But if you see nature, it can be a honeybee, you can see around you. In nature, the structures are self-replicatory and they have a very fine dimension tolerance. They are almost similar looking, similar size, and so on. So we took this inspiration and started working on microbial methods or utilizing living species to make nanoparticles. Now, the slide here clearly shows this is one of the first work we started making, quantum dots of MOS2 and also cadmium sulfide using microbe. So we take a microbe, put our salt with this, let it react, and after a certain time, it can easily form a nice quantum dot on the surface of this microbe. Now we can easily separate microbe with the quantum dot using centrifugal separation, and the size plot here shown, you can clearly see different methods of synthesis and the size distribution. Now current method, you can see it not just gives a good quantity, also it has a very narrow size distribution, and it can be utilized for several biomedical applications. For example, we are utilizing it for glucose or H2O sensing, and you can, the transmission electron microscope shown here clearly shows this quantum dot, you can see which form on the surface because of microbe interacting with the salt and producing a controlled size quantum dot. Also, we can extend this to make some of the important carbides which is utilized for aerospace application. So if you know about titanium, tantalum carbides or even niobium carbide are very good for high temperature application, but processing them is very difficult because it takes a lot of energy to make them. Now we can take niobium salt and start with niobium oxide, treat during the environmental condition in presence of microbes, and you can see in scanning electron microscope here and also AFM, you can make almost similar size and thickness niobium carbide from niobium oxide, which is generally found in nature. Now the X-ray, and this is the reactor, it can clearly show this was the niobium chloride salt which we started with. It converts into oxide, and then slowly, because of presence of microbe, it starts becoming black color niobium carbide, which can be utilized for energy harvesting, it can be utilized as coating, and so on. And all of this material, the size, thickness, and dimensions are almost similar to each other. Extending the work, and now as we can make different kind of 2D material, we can make nice suspension of this 2D material, we can produce in large scale, we can produce in energy efficient way. The next task is how to build a complex structure, how to make them in realistic application. And then comes one of the most interesting aspect of engineering is 3D printing now. Now 3D printing, again, the whole work started in 1980s, where people started with lithography and so on. But thanks to computation or computer revolution, where they really integrated those initial work into engineering marvel. And today we have all sorts, whatever you can imagine on a computer or whatever you can draw on computer, you can literally make them in real object. And this is an example very close to your place in IIT Madras, where it was in news all over that they printed a house. Now, again, the whole aspect of this particular slide is that 3D printing enables us to make any complex shape and any structure without any problem, without any human involvement. Now, the question we started asking that, okay, we don't want to print house, but we have, can we utilize this nanomaterial to print complex topology which doesn't exist before? And when I say complex topology means, now tubulins are a carbon-based structure which was predicted in 90s by several scientists that if you take carbon structure, modify carbon geometry, you can make very complex nanostructure. When I say complex means in the whole 3D structure, there is not a flat area you can find. Everywhere it's everywhere it's curved or bended. Now we take this computer generated structure, make them into solid structure and trying to retain the topology, and we put them into 3D printing. Now 3D printer can print whatever you have drawn on this in your computer screen, you can literally print them. Now the question we are asking, in all the polymer composite area, the biggest or one of the most important goal is to have lower density and high strength. Now this density, how you can reduce by creating pores without reducing the load bearing capability. Now we keep on building this complex geometry, and here one of the beautiful example of tubulene where you can see it's not just we improve the mechanical property, we also get high impact resistance. Now, plastic being impact resistance is very rare because generally their toughness is very low, they disintegrate easily. But if you print them into complex geometry, you can see here we exposed to a bullet which is of speed 5.8 kilometer per second, and you can see a solid metal block. If you impact, generally you see a lot of cracks around it, although the bullet stops, but you have a lot of strain at bottom. So the interaction or the strain transfer comes all the way at bottom. Whereas in 3D printed structure, if you see the interconnects absorb the energy, absorb the strain, and rest of the structure remain intact. Now, such kind of interesting things we have keep on expanding, and we have built several structures. For example, what you see here is the zeolite inspired structure. We can tune the literally surface area and change the energy absorption, what you see here. And also we can build several structures inspired by mathematics, equations, which is merger sponge. We can also understand nature, complex structures. Like unlike human, nature doesn't make a flat structure. It always makes complex shape structure. For example, ant hill. If you see ant hills, they're not flat at all. We have done the study here where we try to understand how ant hills, and what we found is the topology of ant hill is complex just to save the ants when they are either under the high load or they are under rain and so on. How the house is built or the ant hill is built in such a way that ant can be safe in extreme condition. We try to understand using 3D printing. And remember, all this structure can be utilized, or we have utilized already, for water treatment, catalysis, template, and so on, where we have a high surface area, low density, and reasonably high strength to retain the structure. We utilize this porous structure as a template where we can grow some of the nanomaterial, for example, zinc oxide and so on, which can treat the water. This 3D printed structure are coated with certain chemicals which can absorb nanoplastic or microplastic. So all this 3D printed structure can be utilized into this functional or environmental application. Now, the question is, can we 3D print nanomaterial? Now, most of the printing methods cannot, it's difficult to produce nanomaterial 3D printed structure, but except one where we can utilize the ink of nanomaterial. And this printing method I'm going to discuss is direct ink writing. So what we do, it's very similar to our old method in India where we make a slurry or gel of a material and press under force, they start coming out or start printing it. Now, if you connect this extruder with a 3D computer, which control with a robot and with a motor and computer system, we can print them to a certain shape. And what we are showing here, the first thing we did, we 3D printed graphene. So we took graphene, make them ink, and then we tuned the rheology right with a binder and other additives such that we can make a nice extruded structure. Now, if you can do that, you can see here we have printed the complex shape where we have a high surface area. The scanning electron microscopy shows that these layers are intact and they are nicely aligned. Once we do a simple treatment to get rid of additives, we retain the carbon structure, which has good strength and a good amount of ductility. Now, the ductility comes from the 3D X-ray image shows that the ductility is coming from the interconnected carbon, which try to lock when the structure fails. And we can keep on doing it in cyclic condition. The structure can retain the load, and some of the small voids and cracks can be also be closed up while doing the loading condition. They retain their porosity also under certain load, and they can be utilized for most of the conducting structure what we utilize today. And we can start aligning them while 3D printing. We use graphite mixed with the polymer and try to print them. Now, the interesting part is if you do the right processing condition, we can align these carbon or graphite particles into polymer, and we can establish a relation between different processing conditions so that we get aligned fiber. Now, if you get aligned carbon particles or reinforcement, we can have a tunable mechanical property. You can see here we can get high strength in certain direction. We can also tune that as well. Now we can make different pattern using 3D printing, and we can engineer the mechanical property in certain direction, which was not possible. Apart from that, this direct ink writing also avoid void, porosity, and defect which cannot be removed, or which is very difficult to remove using conventional methods. So while printing, we get rid of those defects as well. The last part here is we are going to quickly discuss about sustainable 3D printing, where I'm sure most of you, if you have seen chicken, we make chicken curry out of it. After eating the chicken, we dump the bones. Now, these bones are of no use. Generally, they are dumped and just thrown out. Now, the question is, can we utilize such waste for something impactful or something useful? Now, biomaterial development is a very interesting field of research where people utilize different chemicals to synthesize hydroxyapatite or calcium-based material. And then they need to modify the surfaces to get biocompatibility. Now, the question is, instead of making those chemical synthesized material, if you can take this kind of, material which are coming from living organism, if you can extract the material from here and then engineer them, then we can make eco-friendly, sustainable material. Now, we take the chicken bone and do a very green chemical treatment. And we clean it up first, put them into citric acid, and let it be there. When you let it be there for a long time, if you get the right chemistry, you can make this nice fine powder out of chicken bone. Now, again, there are a lot of methods before people try to crush it, but the problem when you do ball milling and all, you end up modifying the shape, you may end up contaminating, and all sorts of problems can come. But this non-destructive method, where we don't put any energy, you can easily, just by chemical treatment, you can extract this powder. It can be easily scaled up depending on your reactor. You can make as large size as possible. If you look at it in scanning electron microscope, you can see these nicely flat particles, which are very interesting. They are made of calcium. They have a very narrow size distribution, and we utilize them to make the ink. Now, once you make the ink with the right amount of binder and additives, this ink can be utilized for 3D printing. You can see here we can 3D print complex shape, and we can optimize the chemistry, print in any possible shape, and utilize their mechanical property. We have shown here as a demonstration in the work that kids' bone is very difficult to replace, because depending on age and their background, this can change. So there is no right dimension of this bone of the kids. So what we did, we took the real broken piece, scan it up, and then 3D printed structure. Now, because of the fine particle, the surface roughness or the dimension tolerant matches exactly with the real structure. As a result, it can be easily replaced. And again, it's a green method. We don't put any additives, harmful additives. So hence, it can be directly implanted into the living. Also, this chicken bone particle can be utilized into an energy harvesting device. So what we do here, we take the chicken bone particle, a chicken bone extracted particle, we call it CBE, which can be printed on a substrate, and copper is the substrate we utilize, coat it up, and then we start putting force. Now, once you put force, we see that they start producing voltage. When we did detailed study, we can calculate, and we observe that the piezoelectric coefficient of this chicken bone extract particle is as comparable to some of the conventional piezoelectric material like barium titanate or PZT and so on. Now, all these piezoelectric material is utilized for energy harvesting. Now, they are involving a lot of chemicals. Some of them are toxic. Some of them need a lot of energy. But here, you have a natural material. You don't need to do anything. Just mix with it. Just 3D print into the right dimension, and you can get a very high energy harvesting. These are the cover pages which highlighted our work, and we are thankful to all the collaborators and all the people who work with us and helped us in making this work. And these are the 4 different areas where our group is working: the 2-dimensional material, 3D printing, uh, trying to make alloy and structure, which I have not discussed today, but we do work on alloy development, try to make high temperature structural material, and the sustainable material development. These are the 4 areas. These are different labs which is here. Again, most of the characterization we utilize our central facility, and these are some of the processing setup what we have in our lab to process this material. With that, thank you. If you have any question, you can drop my email, or you can check our website to see what is recently, what are the work which we are doing. With that, thank you. We can take questions.
Thank you.
So,
Yes.
yeah.
Thank you. Thank you very much for the wonderful session, sir. Now, I may request the fellow participants to drop your queries, or you may ask Professor directly. The session is open for questions now. Participants may unmute your mic and ask your questions directly, or else you may drop the questions in chat box so that we will read it out. Any questions from participants? Please let us know.
Okay.
Any questions?
Okay, I see Sandesh Kumar. Okay. Okay, looks like a lot of questions coming up. So the first question is by Sandesh Kumar about sensor applications. Sandesh Kumarji, yes. See, whenever we talk about high surface area material, uh, sensing is one of the key aspects. Now, there are different kind of sensors. I will restrict myself to the chemical-based sensors where the material interact with the sensing element. These 2D materials are excellent, and if you can 3D print them into a right surface area, we can make robust, flexible, adjustable sensors, and that is where large thrust is going ahead. What is the future scope in bio 3D printing? Yes, thank you, Balaji, for the question. The bio 3D printing, again, it's a huge area. There are a lot of work happening around the world. But before we go to 3D printing, the biomaterial aspect is something a lot of emphasis is going on. At the end of the day, 3D printing is just going to enable us to make complex structure or required structure. But the material aspect has to be tuned, has to be engineered in such a way that we can easily, we can control it, or we can make them into right required composition or chemistry. But yes, as of now, bio 3D printing is one of the biggest thrust area across the world where 3D printing shows promise, because again, every human is different, and their parts are also, or the the architecture or geometry is different. Now people want to have a customized replacement. It can be bone, teeth, or any structural component. So yes, 3D printing is becoming very important there. Now organ 3D printing is something which is way complicated. I'll not comment on that because I have not worked there. But yes, that's an area of interest by several researchers around the world. Yes, Sandesh Kumarji, I have dropped my email ID in the slide. I'll just drop it here as well. So any one of you, if you need any information, please feel free to drop an email to me. Oh, yes. Okay. Dr. Suresh Ji, he has asked the question, effect of nanographene in aviation biofuel. That's a very interesting question. And we have just recently one work which we have done. In aviation fuel, in certain places, water is a big problem. There are small droplet of water which does affect the properties. In graphene-based filters, and Professor Rahul Nair, he's working extensively in this area, where they are trying to separate those water without losing any fuel. So graphene looks promising. With certain functionalization or certain engineering, it can filter or clean the aviation fuel. They are working on mostly, as I told you, water filtration or water removal from there, but there are many other applications also can be looked at. Yeah. Hello. Okay, Madanji, if you have any question. Okay. Any other question?
Yes, sir. I have a question actually. So you spoke about the usage of biomaterials like chicken bones for medical applications, bone replacements. So since it is a biomaterial, organic material, will it not react with the human body? Have you studied any like corrosive behavior of such 3D printed material when it is implanted into human body?
Yes. So we did, again, I have not discussed all the detail in the slides, but if you see the paper, we have performed the, generally the first thing they do is look at the absorption or expansion ratio, how much water or how much fluid it can swallow, what is the dimension tolerance. So the chemical interaction has been studied and it shows it's within the tolerant limit, as reported in the paper. Also, we have seen the cell growth is way better in our chicken bone extract particles, just because, again, these are extracted from natural sources. So the cell viability study or MTT assay study has been done, which shows way better than any existing hydroxyapatite based structures. Again, it's nothing surprising, because again, if you extract things from chicken bone or chicken part, the chicken bone extract particles, they will have better biocompatibility as compared to any other material. Now, one of the interesting aspects which we have not talked about, which you can ask the question saying that, sir, is it only calcium hydroxide or there are other things? And that is something which was very exciting to us. When people are making calcium hydroxy based material, they're just restricting to calcium. But in chicken bone, we see several other elements which nature has engineered and put them in a right composition, right chemistry, that it works in a perfect way compared to artificial material. So, but again, the question is, can we synthesize chicken bone artificially? The answer will be, it will be very difficult, because the chemistry, the structure is very complicated. Rather, we can directly utilize it as it's a waste material. It can be utilized for building more interesting, not for just bio implants. We can utilize for any other ceramic coating as well.
Okay, sir. Thank you. So any more questions from participants? The session is open for another 5 minutes for questions. You may please. Okay, then, so in that case, can we conclude the session, sir?
Yes, if there is no question, thank you
Yeah,
all.
yeah.
Thank you so much for the opportunity and hope to see you all some point of time in near future. Thank you.
Yes, sir. Please allow me to, excuse me, sir. Please allow me to invite Dr. C. Prabha, Professor and Head of the Mechanical Engineering Department, Arjun College of Technology, Coimbatore, to deliver the vote of thanks for today's session. Over to you, ma'am.
Thank you, sir. Good morning, everyone. I deem it as a honor to propose the vote of thanks in this 5 days FDP. I extend my sincere gratitude to the management, head of the Department of Aeronautical Engineering, and the organizers of Hindustan College of Engineering and Technology, Coimbatore, for organizing this 5 days FDP on advancement in aerospace materials, manufacturing, testing, and characterization 2.0. My heartfelt thanks to our distinguished speaker of today, Dr. Chandra Tiwary, Assistant Professor, Metallurgy and Materials Engineering, IIT Kharagpur. So your talk was very informative and it was very interesting also, sir. Your expertise has illuminated new pathways for innovation in this field. Last but not the least, I thank all the participants for your active participation. Thank you.
Thank you. Thanks a lot. Thank you, everyone.
Thank you.
Okay.
So thank you very much for attending the session. Hopefully, you have had a great experience today. There is a question from Guru M. I am afraid a professor has left already. So I think he has shared his mail ID in the group, in the chat box. Mr. Guru, if you can able to look at the chat box, the professor's mail ID is there. So you may please ask the question directly, and you can send your queries to his mail ID. And regarding the feedback, feedback link will be shared in the group. I request all the participants to share your feedback regarding the session, which will be sent to the today's speaker. And regarding the afternoon session, I wish to inform you that we have preponed the session to 30 minutes because the afternoon speaker has some sudden work, so that she couldn't able to present on the scheduled time, which was 2:30 p.m. in the afternoon. So we have preponed it to 2 p.m. in the afternoon. So for your information, the afternoon session will be presented by Dr. Indrani Sen, Associate Professor, Metallurgical and Materials Engineering, Indian Institute of Technology, Kharagpur. The details of the topics will be shared in the group. So I request all of you to join for the evening session, the afternoon session, by 1:55 p.m. sharply. Okay. Thank you very much. Thank you for joining. You may leave the session. Feedback போட்டு வரீங்களா குரூப்ல? Well, the feedback link is posted in the group now. Well, the session is over now. You may leave the group. Hopefully you have received the feedback link. It is in the chat box. It is in the chat box. Feedback link not yet opened. Once again,